So like we say, the duration of a clock cycle actually is the reciprocal of the clock speed. But what is the clock speed? So the clock speed actually is the CPU speed. So for example, I just say, for example, now I have one i3 CPU. My i3 processor with 1 gigahertz speed. So when we say the 1 gigahertz speed, 1 gigahertz actually means the speed. And gigahertz mean in 1 second how many operations. So 1 gigahertz actually mean in 1 second, every per second, we have 1 giga operation. So what is 1 giga? Right, 1 giga operation. 1 giga mean 10 to the 9th power. So remember, we start from K. K is 10 to the 3rd power. That's K byte. Megabyte. Megabyte is M, is 10 to the 6th power. So when we talk about gigabyte, that's 10 to the 9th power. Let me write down here. So whenever before you hear about the K byte, that means 10 to the 3rd power. Megabyte is 10 to the 6th power. Gigabyte is 10 to the 9th power. So of course, terabytes is 10 to the 12th power. Okay, so back to our Core i3 processor. If you have 1 gigahertz speed, that means in 1 second, you can have 10 to the 9th power operation. That's a lot, right? Good. So then 1 second, you can have so many operations. So on the other hand, one operation is how many seconds? So what we need to know is we know the speed, but on the other hand, we also can know how many seconds for each operation. So that's earlier we say the reciprocal. Okay, so 1 second you can have 10 to the 9th power operation. So if you flip that, each operation actually is 10 to the, you flip that. So don't forget, when you flip that, the exponent, when you flip that from the denominator to the numerator, they become negative. So that's why 10 to the 9th power become 10 to the negative 9 power. So 10 to the negative 9 power in second equal to 1 nano for each operation. So on the other hand, whenever you know the speed for your CPU, you also can calculate what is your clock duration. So you just need to flip your speed and convert the hertz become operation per second. So then the clock time actually means each operation will take so much time. So then each operation actually just 1 nanosecond. 1 nanosecond actually means that's 10 to the negative 9th power second. So that's each operation, they all need to follow one operation. One clock, one operation. So the clock is used to trigger the events. So what does that mean? That means any operation only do in one clock time. No matter they are faster, they still need to wait one clock time until the next one. Okay, 1 nanosecond, I read the data from the memory. 1 nanosecond, I add two numbers together. 1 nanosecond, I overwrite the data in some location. So that's all we call the operation or instruction. So then after you understand that, we will see the picture like here. We will see really how the CPU will work. So here we will make our CPU even a little bigger. Okay, so earlier that's the CPU we talked about. But in here we make that more specific. Like earlier we told you, in this CPU, right, I have control unit. That's the CU. In the CPU, we have the arithmetic logic unit. In the CPU, we have register. And in the CPU, of course, we have the clock time. Okay, but this clock time, actually the clock just control the time. So you are not really see where's the clock. But then afterward, you will see even more. Okay, so what does this mean? When you have your control unit is we using to coordinate the instruction, right? So those instructions actually they have instruction queue. So this instruction queue is waiting in line somewhere. So this instruction queue, how do we know which instruction to process? We have an instruction pointer we call IP. So this instruction pointer will point to the specific instruction in the instruction queue. So when they need to work on that, they were using the instruction number to decode into the code cache. So then this code cache, they will decode the instruction. So you decode this instruction, the control unit know how to do. For example, you see we have so many instructions in the queue, right? But those instructions in the queue actually just like before we show you, they are like machine number, like here. Okay, I mean to do move EAX with 5. We add EAX with 6. So then remember, you see here we have the machine language. Machine language actually is read by CPU. So earlier when we say the instruction interpreter is like the B8. The B8 need to be interpreted to know this instruction number mean what. So after we know that, then we will process this instruction. So here this B8 is where we will do the interpretation. The instruction pointer point to the B8. That's the next instruction we want to work on. But we don't know what is B8. So that's why we need to have the code cache to interpret and decode this instruction mean. So once we know this instruction mean for what, right? So control unit will process that. Control unit know this instruction, should I send to the arithmetic ALU unit to process, or I need to read from the register. Okay, so then, or actually we still have another one is the floating point unit, because ALU is working on the arithmetic and the bitwise operation. So on the other hand, they're working on the integer part. So then we have the other unit is the floating number. Floating point, that means if you have a decimal number, we need to process separately. But no matter what, after I decode that operation, the control unit will take over and talk to different units to see how to work on that. So after they work on that, they will work on the value and the data, right? So then they have some temporary location to save and store the data. We call data cache. So in the unit, in the CPU earlier, we see control unit, we see register, we see ALU, and also actually we have the code cache and the data cache. So code and the data, you can see that. So you can understand what did that mean. But the cache actually is reside in the CPU. They will be faster to access. So if necessary, they need to pass in the data through the memory. So they will go through the data bus. So go to the memory. Or they will only know the address. They will pass in the address to read the memory, to find the location, then pass the data. So that's how the CPU look like. So this CPU look like, so now we just interpret to show you. Let's assume we have one instruction pointer register. So that's earlier we said the IP instruction, IP register. They're holding the address for the instruction. So we just, for example, the next instruction we want to work is B8. Okay, so after we know that's B8, we see what happened in the step in CPU they work. So the first thing, after you know the location for the instruction will work, right? CPU has to fetch that instruction from an area of the memory we call the instruction queue. Now, because we know the instruction queue, they will queue. On the top of the queue will be the next instruction we will work. So then after you get the queue, you increment the instruction pointer, you go to the next one. So after you got the instruction, so CPU will decode that instruction by looking at the binary bit pattern. They have something to look up. The bit pattern may reveal the instruction has operand or without operand. So actually it's only the instruction itself know how to do that. So these two steps is earlier we show you here. You see your instruction pointer. So then you have the decoder. CPU asks them to find out how they will do. So once we know what this instruction will do, will they have operand or not, then we do the next one. If you have operand involved, CPU will fetch that operand from the register and the memory. It also involves some address calculation. So that's why you see here, after we have the instruction ready, right, control unit will tell them to work on that. If you have operand you work directly, okay, we access the value from the register. If not, you may need to go through the data bus or address bus to get the value. So then we need to see, depends on how the instruction look like. So that's the part 3, step 3. So then you see CPU execute the instruction using any operand value if necessary. Then they will update a few status flag. So later we will show you the status flag. Those status flag actually is part of the register. So then you see here, when they do the calculation, right? So those calculation possibly from the register, possibly from the floating point unit we need to process. So all the data we need to access from the memory. But no matter what, after they process, right, they will update the data. They will update the status flag. Then after they done, if they have an output, so they will store the result into the execution to the operand. So that's your instruction execution cycle. Then that's how the picture look like. To see if you can understand like this. Write down any question you have, then we can answer your question. So let's talk about a little more about the code cache and the data cache. So if we can access the data from the code cache or data cache from CPU, there will be much faster instruction than we access from the memory. So because when we have the cache memory, they are stored the most recently used instruction and the data in the high-speed memory. We call cache. So why they are high-speed memory? Because they are actually reside in the CPU. So the high-speed expensive static RAM both inside and outside the CPU. Okay, so they have the first level cache is in the primary. We say the primary cache that's inside the CPU. They have the level 2 cache that's secondary cache outside the CPU. That's also usually you see the memory. What do we have here? So of course, if you can find that within the CPU will be faster than the secondary. But sometimes if you cannot find that from the first level cache within the CPU, we have to go through the memory. So that's why here we say the cache hit actually means the data to be read is already in the cache memory. If not, they are not reside in the cache memory. Then we need to go through the data bus or memory bus to access the data. So when we access the memory from data, you can see here, we have two different buses. Sometimes if you know the data, you will save in somewhere in the memory, so then you will through the data bus to the memory. But sometimes in the code, we maybe only know the address. So we need to access the address bus to know which location I will read the data from memory. So after that, the data you find that you will pass into the data bus, then the data back to the CPU to process. So that's how you will look like. When you're reading from the memory, basically you have multiple machine cycle need to require. So it's not only one instruction, like we say, one instruction for one operation. If you need to read through the address, so you need to pass in the address, then get the data, then pass to the data bus. So when you're reading from the memory, they respond much more slowly than the CPU because they have a couple things to do. The first thing, if I only know the address, I need to place the address of the value through the address bus. So this address bus will be accessed from the memory to see the data. So then we'll need to waiting for one clock cycle from the memory pin to memory chip to respond. So copy the data to the data.